This is lecture number 19, the same chapter what we have started, and we are studying the modulators. In the last lecture, we studied about the electro-optic modulator, and here in this lecture we are going to study about the acousto-optic. Acousto-optic, it's definitely it has a link with the sound waves, and somehow it's more practical in some of the lasers, and it's somehow it's cheaper than the electro-optic modulators. So what do you see here in this diagram? This is the actual acousto-optic modulator, okay? And this is its function. Like this is RF source, radio frequency source, and here is a piezo electric crystal, okay, which vibrate, and this is quartz crystal, and this vibration produce the sound waves here inside acoustic waves, and different layers are developed here, and because of these layers of waves, the diffraction of the light is happened. So in simple words, actually it become a diffraction grating when RF signals applied to the piezo oscillators and the waves pass through, okay, because so many waves pass through and it acts like a diffraction grating. They are saying here it's the simplest and most common. I'm not saying it's very simple, but maybe as compared to the electro-optic, maybe it somehow simple, and it's commonly used in some kind of lasers. Acoustic waves, sound waves, okay, it can be a radio frequency waves, okay, in the megahertz range or something like this, and it's originate from a piezoelectric crystal, this one here, okay, and this crystal, what it does, it generates the surface acoustic wave in a crystal, in a quartz crystal, you can say, okay. RF signal is applied here, the piezoelectric crystal, and this crystal produces what it produces. It produces a sound or radio frequency waves here in this quartz crystal, okay, and this radio frequency waves here, it's generated, and this quartz crystal acts like a diffraction grating. Here this wave is transmitted through a quartz crystal. This is a quartz crystal here, and induces a strain in the crystal. Strain, if you see that, okay, strain here like this, like this, like this, or in this direction, can be like this, can be like this, okay. You people must have studied the solid state physics. You should have known about the strain, which changes its refractive index on a localized level. Refractive index is changed, okay. So diffraction grating, okay. So a refractive index is changed when the strains are generated here, and so that is why the light is diffracted in different directions, okay. The acoustic waves creates rarefactions and compressions, okay. Rarefactions and compression, what happened in the air when the sound waves travel, okay, that is rarefaction and compression. And what it does, it changes the density of the crystal, okay. Rarefactions, okay, rarefaction and compression, rarefaction, compression, rarefaction, compression. So in this way, what happened, that the density of the crystal is changes, okay. You can see in the figure the end of the crystal is either cut at an angle or terminated with an acoustic absorber. The end of the crystal here, this size end of the crystal, okay, is either cut an angle, it is with a certain angle, you can see here this angle, okay, or if they don't cut in this way, then they put acoustic absorber. Acoustic absorber, it will help to prevent the standing waves to generate. If the standing waves are generated, then this phenomena will not work and refractive index will not change the way we are expecting. Okay, so the standing waves have to be prevented. So how it is prevented? Well, to cut with a certain angle here like this, you can see, or put any absorber here. So that will absorb the waves and the standing waves will not be generated. And this figure actually is actual acoustoptic modulator. Okay, and this is a cooling system actually here, and the things are inside here. Okay, so in this slide, we see this equation. And this equation is very important. This wavelength, this is the wavelength of the acoustic waves in the crystal. This is the velocity, not velocity, sorry, speed of sound in the crystal. And this is the frequency, okay, simple frequency. Wavelength, speed, and frequency in the crystal. Okay, so these things are mentioned here, if you can see. Important thing to understand this diagram, okay, or figure you can say. Once we give the RF signal here, this piezo transducer or piezoelectric crystal start working. It's vibrating, okay, with a certain frequency. What will be the radio frequency here? And this frequency will introduce acoustic waves in this crystal. That will be like this, like you can see here, 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 here. This, because of this acoustic waves that we studied in the last slide, there is a compression and rarefaction. Like in the air, when a sound is travel, is like somewhere compressed, somewhere rarefaction, somewhere compressed, rarefaction. So you can see here compression, rarefaction, compression, rarefaction, compression, rarefaction. Okay, and strains are produced. This is called strains as well. So for in case of a compression, the index of refraction is high, and in case of rarefaction is low. Okay, so this is one of the reason how the light is deflected. It can be undeflected, it can be deflected, or it can be deflecting according to the refractive index, whatever it is generated. Acoustic waves. These acoustic waves are generated, and because of these acoustic waves, this thing happen, compression and rarefactions. And you will see if there is an incident beam is coming here. This is deflected one, okay, deflecting at the same angle like here, and other one is like undeflected. This is normal phenomena which is undeflected. This is deflected one, this is undeflected, is not a normal refraction. Okay, so there are two kind of diffraction happening here. One is called Bragg diffraction, and other one is called Ramannath diffraction. It depends on the incident angle of the beam. Okay, that we will see definitely in the coming lectures. So if I explain in Urdu very simple that कि ये आपके पास एक क्वार्ट्ज क्रिस्टल है, और इस क्वार्ट्ज क्रिस्टल में जो साउंड वेव अकूस्टिक वेव्स प्रोड्यूस की जाती हैं वो इस पीजो ट्रांसड्यूसर या पीजो इलेक्ट्रिक क्रिस्टल होता है उससे की जाती है. इसको आरएफ सिग्नल दिया जाता है, इसमें रेडियो फ्रीक्वेंसी ये वाइब्रेट करता है, और ये इस वाइब्रेशन से क्रिस्टल में जो अकूस्टिक वेव्स जो पैदा होती हैं, और उससे कंप्रेशन रेयरफेक्शन का इफेक्ट होता है, और उससे रिफ्रैक्टिव इंडेक्स चेंज होता है, और लाइट कैन बी डिफ्लेक्टेड और कैन बी अनडिफ्लेक्टेड. सो टू अंडरस्टैंड इस फिगर को समझना बहुत ज़रूरी है कि रेयरफेक्शन और कंप्रेशन, ओके, द स्ट्रेंथ जो बनते हैं आपके, और दिस इस इक्वेशन को स्लाइड पे कुछ पॉइंट्स दिए गए हैं. That's what I am going to explain here now a bit. In the Bragg regime, light beam is deflected by alternating layers of differing refractive index. Compression, compression, rarefaction. Okay, this is what it's telling here. In the case of AO modulator, the acoustic waves inside crystal sets up parallel planes of varying indexes of refraction. Simple thing. In case of acoustic modulator, definitely we are studying the acoustic-optic modulator. The acoustic waves inside the crystal sets up the parallel planes of varying index. That is compression, rarefaction. Again, I'm saying it's like this, like this, like this, like this, like this, like this. So, which like the parallel planes of atom in the crystal. That is, as I told you, generate the Bragg diffraction. What is Bragg diffraction? Okay, you must have studied in the solid state. Other point, the wavelength of acoustic wave in the crystal, that says correspond to the wavelength of the incident light beam. The wavelength of the acoustic waves in the crystal correspond to the wavelength of the incident beam. So whatever acoustic waves are generated, it has to be correspondingly wavelength of the incident light beam. What kind of incident beam we are going to use? Okay, what wavelength we are going to use? So according to that one, that acoustic waves are supposed to be generated. So this is, I mean, when you buy the acoustic waves acousto-optic modulator, it comes with a box. You can adjust the frequency. Okay, so you can adjust the frequency, you can adjust the acoustic wavelength, because not it's not like a universal that it's for all the wavelength of light it will work. So this is what it's saying here. Incident light beam on an acousto-optic modulator crystal is deflected only when an acoustic wave is present in the crystal. Only when an acoustic wave is present in the crystal. So what is saying? Incident light beam is deflected only. I mean, if it is off, there is no RF signal, then there is no acoustic waves. Then it will not be deflection, nothing. So it will only be, you will see when the acoustic waves are generated. And when acoustic wave will be generated, when the piezo in transducer or piezoelectric crystal will be working. Okay, so this is driven by RF, so radio frequency source. Now we move further. What do you see here? There's a mathematical relation. Okay, and this is, if you have studied the Bragg diffraction in a solid state, you can easily understand the things here. What it's saying here, the deflection can be expressed in a manner similar to that for optical diffraction grating. Similar equation when we explain the diffraction grating, how light reflect, what is the angle, etc., etc. So this equation is similar. So is 2 lambda here, sine theta b, lambda and n. So this wavelength in the crystal, this wavelength in the air. And theta b is definitely a Bragg angle. So from here you can calculate the wavelength inside the crystal if you know the Bragg angle and the refractive index and the wavelength, obviously. Now what it says here, when the equation is satisfied, when this equation, this one, is satisfied, how to satisfy this equation? It depends on a certain wavelength. Okay, so when this equation is satisfied, reflected wave from each parallel plane, which is generated by because of the compression refractions, will be separated by phase shift for exactly 2 pi here, 2 pi here. Okay, so reflected waves from each parallel plane will be separated by phase shift of exactly 2 pi, okay, one period, so that the constructive interference take place. So 2 pi, okay, so constructive, if it is pi, then a destructive interference, okay, constructive interference like this, constructive interference. If you have like this, destructive interference, okay. So these here, rarefaction and compression, these parallel planes are formed, okay, and is separated exactly to produce a phase shift of 2 pi, so that to have a constructive interference. But this thing is only happen if the sound wave is generated very nicely, accurately, okay. The exit beam is deflected out of the crystal at the same angle as it enters here, okay. This is deflected out of the crystal at the same angle as enters, this angle, here, this angle here, okay, this angle, as well as being useful as a modulator by deflecting the intracavity beam out of the cavity, hence preventing amplification when the words of book. In this case, the light is entering like this, okay. There is one beam which is undeflected, okay. There is one beam which is deflected. So deflected, if you want to capture the undeflected, that will be go out of the you have a cavity, okay, and this will be amplified. Or if you want to use this one, can also use, you can take it out, this one, out of the cavity, it depends. This is the problem. Example is in your book, and this example you have to calculate the angle of deflection. To find out the angle of deflection after passing through the crystal, the light, and there are some things are given that this is the frequency 28 megahertz, okay, and they are saying the incident ray of light is helium neon laser, and speed of sound in a quartz is 3750 meter per second, and this quartz having a refractive index of 1.46, and calculate the angle of deflection caused by this modulator. So simple thing is that first you need to find out the lambda, the wavelength, otherwise you cannot apply this equation, okay. So find out this, you need to know the velocity of speed of, sorry, not velocity, speed of sound or frequency, and speed of sound is given here, and the frequency is also given here, which is 228 megahertz. So the wavelength is coming 134 micrometer, and if you substitute this one here, and you get the answer, which is the deflection angle. So this is the how you can find out the deflection angle if you're using certain crystal, but you need to know certain data, speed of sound in the crystal, and refractive index and frequency, etc. As we have discussed and the last before the last slide actually, that there are two kind of diffraction occurs, okay. One is a Bragg diffraction and one is a Ramannath. Previously we studied that is the Bragg deflection, where the theta b is mentioned. Here we'll see that, and I also mentioned it depends on the incident angle. incident angle. Okay, if the incident angle is like this, making certain angle, then definitely it's a Bragg diffraction. But if the incident angle is straight like this, then it's called Ramannath diffraction. And in this is exactly like a diffraction. If you have a transmission diffraction and the light pass through, the pattern, output pattern will be like this. Okay, so these waves are generated here, and compression, rarefaction, compression, rarefaction, compression, rarefaction. Okay, and you can see the because of the different refracting index, the light is deflecting in the different directions. Center one is undeflected actually, and other one is deflecting. Okay, this is Ramannath diffraction. The previous, what I explained, that was a Bragg diffraction. So what it's saying here, that Ramannath diffraction occurs when the incoming beam is aligned perpendicular to the alternating layer. It's perpendicular. Okay, this is a layer, these are the layers, and beam is like this, exactly perpendicular. Okay, 90 degrees. Okay, and which act like a parallel slits. You can say it's parallel slit, light is passing through in a transmission diffraction getting. Okay, so in this region, region, the diffraction is modulated, not modulated, modeled to occur from a thin acoustic wave being inside the crystal. Okay, so what exactly happening in the simple words? This is your piezo transducer. These are rarefactions and the compression are generated. Okay, same. And this is acoustic waves, and this is the incident beam, and the light is having, because of this compression and rarefaction, different refractive index, so it is reflecting in the different directions. Okay, some are center maybe and deflected. You can find out the angle with respect to the first one. This kind of refraction is called the Ramannath refraction. Okay, so what exactly they are saying here in this sentence, the diffraction is modeled to occur from a thin acoustic wave beam inside the crystal. So this is how thin acoustic beam here is passing through. Okay, that's what they want to say. Now the angle of diffraction is quite different from Bragg angle, obvious. Okay, and incoming light beam is deflected in both the directions, like here, 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 away from the plane of incident beam. Okay, that can be like in case of diffraction, first order, second order, third order, fourth order, something like this. So multiple higher order diffraction may occur. Higher order diffraction, one, like here will be, here will be, and here will also be something, and here will also be something. So this is how Ramannath diffraction you can explain. This is the actual picture as I mentioned. This is acousto-optic modulator, and this is a cooling system here actually. This is acousto-optic modulator here, but it's not shown from inside, so you cannot really guess what exactly going on. But it has the same thing which I explained actually before. So acousto-optic model is definitely can be used as a Q switch. When it's turned on, it can deflect the light. When it's turned off, the light pass through. The simple thing. Okay, and this is what is mentioned here, that allow modulator in this regime to act as a switch. Okay, so when inserted in a laser cavity, the diffraction caused by the acousto-optic modulator, so Q switch, what it happens, causes a portion but not all of the intracavity beam to be deflected. Part of the light is deflected. Okay, part of the light will be deflecting away from inside the cavity, so it is not reflected into the laser medium. So we want to take it out from the cavity. Okay, so this which is deflected, we will not be amplifying anymore. So in this case, if it is not amplifying anymore, it means spoiling the laser action. Okay, it spoiled the laser action. So the Q switch, or the Q of the cavity, falls from its normal value to much lower value as losses increases in the cavity due to diffraction. When the light is not entering in the cavity, definitely losses are increasing. Okay, it's building of the population inversion. Okay, and when the light will pass through, you can have the giant pulse. Okay, so when you turn on, light is reflecting. When you turn off, light pass through. And other things can, it depends upon the installation. How do you install your system? How you configure your system? You can use light, the reflected light, or you can use undeflected light. And these things are is tried to explain here. More detail you can definitely see in the book. The modulator requires an RF driving signal, definitely RF circuit you have to make, and then you have to attach with the transducer at a frequency of 27 to 28 megahertz. Okay, usually this frequency is used, but it can be tuned, and minimum power of 10 watt. So most of the commercial Q switches operate at frequencies of 27, 24, 24, 27 or 80 megahertz. That's what I'm saying. It depends for what laser you are going to use, what wavelength, and driver power level from 50 to 5 to 50 watt. Here you see the beam. Here is the deflection, and here is the nothing. So this is a test with the YAG laser. This test was done with the YAG laser. Okay, so what is that? In this test, the output beam having passed through the device, okay, observed with the RF driver signal on and off. Okay, when the signal on or off. When the signal on off mean acousto-optic modulator is on or off. Okay, so what is saying that diffraction pattern showing strong first order, weak second order components is clearly visible when the RF is energized. This one, these things. Okay, this is diffraction pattern, second order, third order, fourth order, and so on. Okay, so this is how it works when the light is passing through and you turn on the switch and it energized. So in this case, you can clearly see the diffraction, and you can deflection. You can. It depends on your alignment and configuration, which beam you want. And if it is off, then only one light is passing through. Okay, off and on. Okay, so this is how the diffraction pattern is produced, and this is how, and the only one light is passing through.